All right, so let me start with the questions. Some are from yesterday. Let's take this one first. Yes, I'm recording now, and I'm also live streaming now, I hope. So if you ever can't make it to class, you can join in from home. There's no good reason not to. Come on in, come on in. Find your seat. Sure.
Where is the live stream located?
So there's a link on my website that always has, it's the same link, my website, wild-inter.net/live. That always has the latest live stream. That link is also on Canvas, so you don't need to remember much. And the recordings, I'll usually just briefly cut out the different chapters and put them on YouTube separately. So live stream is still there somewhere, but if you don't break it up into chapters, no one ever finds it again, including myself. I talked about textbooks, but that was off the record. So the module homepage has lists for each unit. There's no single textbook. I brought the one for the unit 0 if you want to take a look at that. All of them are on the reading list, so the library should have some way for you to access them. In some cases, there's just a single physical copy somewhere in the basement of the library, but it is there. I hope, well, if you need more of those, let the library staff know. There's funds to offer more books if they are used, but if they're always just in the basement, then they won't order more. Not all are textbooks. Sometimes the sources are a bit more recent because we cover a few things towards the end. I haven't made it into major textbooks yet. There will be some other sources for that. Lecture slides are on the website as well. I try to upload them before the sessions. Unless there's last-minute changes, they should normally be fairly stable. At the latest after the lecture, they will be on the website. That question concerns the prior knowledge survey we did on Monday, or some of you did between Monday and now. And there's a few questions about programming. We don't need a lot of programming, just a little bit in the assessments, but you can get a long way in those assessments without writing a single line of code. Only at the very end you have to submit a bit of code, but this can literally be 10 lines. I think is very, very little that you really need to. Now, I encourage you to program, and the solution for some of these are much nicer to find if you program something. We'll mostly use Python because that's the main language in the course. In other modules, and many of you have this fundamentals of programming module alongside with this. So no need to worry too much if you don't know how to program much yet. We won't use a lot. Some of the things I want to keep references in for those people who come with a CS undergrad degree, because it's nice to make these connections to programming and certain programming languages. But they are usually not essential to follow the main part of the module. So this is a good question. The second bit is a good question. Is this necessary? Still not 100% sure. Well, let's do it. I'll show you the code in a sec. This is on the slides from Monday, which you can find on the website. It's also in the announcement on Canvas. So if I sent you stuff on Canvas, that's still in the announcement section. You also get an email, right? Do read your university emails. Goes without saying. Even if they sometimes get piling up a bit. Try to go through them at least briefly. So that code's there. I don't remember it from the top of my head. So here's today's code. I think it's easiest. I'm showing a question on Slido, but it's not refreshing here, is it? can you see the Slido code? So I'm trying to show a poll on Slido. Not sure why it's not showing. Someone was stuck in the Q&A, right? Well, anyways, that's the code. I hope you could see it on your devices either way, just not on the screen. It's gone again. That's a weird bug. Can you see it on your devices? Okay. I'm trying to keep an eye on the chats on Campusfire as well. I think that's all old. Good. I'll leave this up on Slido, but move on to today's topic. Yep.
Before we start, the person who doesn't have prior knowledge to Python or any programming language, can you suggest some references or links that we can use?
Yeah, so the question was, if you don't have any prior knowledge on Python or programming in general, what are good references for that? I mean, mostly I would point to the parallel module that you're doing. Another thing is the algorithms textbook that's linked in Unit 2. Algorithms 4th edition by Sedgwick and Wayne. They use Java, but they have some introductory parts. And for that book, there's also a prior version. I'm not sure if I have linked that. So they have a book called Introduction to Programming in Python. They have it for Java and for Python. I like that one because it has an algorithmic touch, and it gets you started with Python from that lens of using it for algorithms as well a bit. I'll try to put that on. What unit would that be? I don't know. Maybe this is one textbook for the entire module. I could post them on Campusfire. Just remind me again. But mostly follow the other module. I hope it picks up enough speed for you to follow along. It's good that for today we don't need any programming. We're just in the realm of mathematics. Welcome back to COMP526, Efficient Algorithms. We're starting with the second part of Unit 0 and look at some proof techniques. These are some prerequisites that we need to digest some of the statements we make about algorithms and data structures later. Although this unit will not really contain much algorithms and data structures, we take one further step away from that. So this is just about logic and mathematics, but you'll see where it comes back to programming towards the end. I listed a few learning outcomes. You're supposed to know some proof strategies, and it will become clear what these are. It's a given list of things. There's certain types of statements, and each comes with a strategy how to prove it. That's just the scaffold for a logical argument. You still have to fill in the gaps. Specifically, one that's particularly important in computer science is called induction. We'll talk briefly about this later. And we'll apply proof techniques very briefly to give you a glimpse of how you can prove a program correct and what that means. We'll only touch on this very, very briefly. But I think it's useful to know roughly what the limitations and possibilities are there. Before we start with the actual proof techniques, I want to take a slight digression and actually do look at one algorithm. And you'll see also the type of code I'm using on the slides mostly. And this is just as kind of a backdrop for what's to follow. So without much introduction, let me say we have a goal to shuffle an array of numbers. So there's a few things I should maybe point out. This is my notation for arrays. So what is an array? An array is a contiguous piece of memory filled with data, and all these individual data items have the same size. We also usually think of them to have the same type, but some languages don't fuss about that so strictly. But here I'm specifically saying it's numbers. So if you have programming background, think of a C-type int array. That's fine for this purpose, although the algorithm doesn't care too much. The second bit of the notation is this convention for indices. Arrays start at 0 in this module. It's just the computer science way of thinking. It's a pointer and an offset. That's where this comes from. So if we have an array of n numbers, it starts with a 0, and then it goes up to a n-1. And to not always have to write the -1, I'm using this round parenthesis to say that's exclusive, the endpoint, and the 0 is inclusive. If you come from C++ and have worked with iterators and pointers there, it's quite natural to work start point inclusive, end point exclusive. If not, it's a bit of nerd weirdness to get used to, but it's consistent in this module, so it's worth getting used to it. Right, so that's an array of numbers. And one first thing to note, n is just any variable. I want this to work for any size of an array. And the goal is to randomly reorder the array. So shuffle here means you're given an array of numbers, and afterwards it should be impossible to know what the original order was because you just completely randomly rearranged all the numbers. Implicitly, what this says is it should still contain the same numbers, the same multiset of numbers, just in some different order. So we expect algorithms to basically swap two elements. That's the key thing that an algorithm can do, to rearrange elements. Take two indices, take the element here out, take the element there out, put them back in the opposite order. Okay, I mean, this was maybe baby steps for some of you, but bear with me a bit. Now that's a task that arises in various applications. In data science applications, you may often want this to kind of avoid any bias from the initial order of the list. Say you're writing some survey software and you want the answers to appear in random order for each participant. All sorts of things, fairly natural to come up with. More examples. And here's some code that might achieve this. And before we dive into what the code does, let me try to briefly explain what this kind of pseudo code looks like. It's not real code in any programming language. I don't know any compiler that would eat this and spit out a computer executable. But it's fairly close to many languages with slight superficial changes. So I'll write procedure to say this is definition of a function. It's maybe a bit closer to old languages like Pascal. Python would just be def, right? Then there's the name of a function, and it takes some parameters. I'm not usually strict with typing, so that's maybe Pythonic then. Close to what Python does, they don't care about types as much. So there's one parameter of this shuffle function, namely our array. Not a big surprise, I hope. And then we can write different things in pseudocode. So for example, for loops, right, they just go through what is indented further for every value of I in the given range. We have other function calls, and in this case, I'm calling a function random int, and I'm just assuming, postulating that this function exists. And the comment here in English just tells you what I'm hoping this does. Most programs have some assumptions like this, and it's super tedious to always have everything on the slide, and you couldn't read it. So we'll usually work with something like this. There's some things we just assume given, and then we work based on that. And here's the swap operation that I explained before. We expect an algorithm to use this here, and here it's just writing, take the position I and take the position R. These are two variables. They have some integer index in the array. Take the elements and swap them, right? I hope that's fairly intuitive to follow. I also hope that at least by the end of the term, all of you would be able to take this pseudocode and code it up in Python, hopefully a bit earlier than by the end of the term for this simple thing, or take another programming language. This is my approach, to be a little agnostic to what language you come from. Good. So that's about the pseudocode, how we write algorithms. Now, what does it actually do? Well, it looks at each position in the array. That's basically the I. And then it finds a random position for that element to go to, and it swaps it there. Sounds good? That should put it in some random order. Now, okay, let's just do this. See what you could come up with. Oh, Slido is slow today. I had 64 people saying they got the attendance code. So maybe we can crack that up, and that number in the corner. Maybe we can get that at least to 65, 60, 64. Same as before. There's probably a few more in here. Okay, let's define 65 is my goal. And let's briefly just see what you came up with. So a lot of you have seen something like this before. That's great. So you can deal with the code. Not so many are sure about this, it seems, right? More people are confident about the last part. That's the longest statement, right? If it's convoluted in the formulation, it's usually the right answer. So let me lock the results for now, and switch back. Yeah.
Why are the last two questions equivalent?
You mean the last two parts, D and E?
Yeah.
Depends how picky you are.
Like, okay, the second, no, E is going to be like a strict subset of E. So like, if they have the same probability, they have equal probability. You can't have like ordinary with equal probability, or then they have the same probability. E just seems like a more overrated wording. Confused why many people are content of E for fear of content of E. It's like the same statement and same.
Yeah, okay, I get your confusion. So the point was, it sounds like E is a subset of D, and you're right. I mean, I've slightly reformulated this to make it sound a little confusing, but you're very, very right. And so it's kind of surprising that more people ticked E than D to you. Is that what you're saying? Well, it's a subset in the sense of the statement. So it could be that E is true and D is false. In principle, that's possible. In our specific case, D and E really is the same because I'm assuming that this random int does the right thing. That's not the trick of this question. The trick of this thing is something else. And let's have a look at this. So how would we take a step back, forget about the question for a minute, I'll come back to it. But how would you even approach saying that this code does the right thing? So what is the right thing? Yeah.
For each element in the list, it swaps it with a random input.
Sure.
Yeah.
Each element is swapped with a random
So if you
position.
assume that a probability distribution between in 0 and n, then and a uniform probability distribution between 0 and n, that's like what? Let's say uniform random means that for each number 0 and n, random in produces splits each number out with the same uniform probability. So
Right.
1 over n. Then for each element for each a in the sequence, the probability of them occupying each, getting associated with each r, with each number is the same uniform probability. So for like the first element into this, probability of it getting mapped to any number between 0 and n is the same 1 over n probability.
Let me try to summarize this for the live stream. So you're saying this random int gives a uniform number in this range. That's exactly the assumption. And so it seems that every element should be at a random position, and the overall thing is uniform. Now let's look at what happens. So if you take two different elements, that's the easiest kind of thing that is at least doing something. There's two possible outcomes, and these are listed here. And what these bars show is the relative probability of them becoming the result of this function. And it doesn't matter how you start. So you could start with a sorted list if you want. Now, if you do this for 3 elements, something weird happens. So this is starting from the sorted list and then calling this algorithm many, many times and looking how often you've seen the different outcomes. And it gets worse and worse. And then I ran out of space on the slides, but you can continue this. You can even analyze this and show that in a way the relative error. So if this red line, one sec. So the red line is basically the uniform that you would want to see. And so the difference between the peaks and this line become even worse. Yeah.
Is this like a problem because the even n is small? Does this like converge to uniform probability?
Nope, it's not converging to uniform. It's not a problem of small n. And it's even worse. It's kind of diverging from uniform. So there's some things, some orderings that relatively speaking, the probability of them coming out compared to what we want, the uniform 1 over n factorial, that relative difference grows with n, is completely broken. It's startling, right? It looked so well. And I mean, those of you who know this, they might have immediately seen the argument. So I don't want to spend much more time proving to you that this algorithm is wrong. A simple way to do it is to count the number of possible outcomes. That's a nice, rigorous way to show it. So here we're taking n random numbers, and each has a range of n. That's n to the n different things. But what we want is uniform over n factorial. Just by pigeonhole principal arguments, this cannot work out. But this is not what I want you to take from this. The thing is, for showing that the algorithm is broken, all that's on the slide is enough. It doesn't work for 3 elements. What the, right? I mean, that's not good. Even if it's fine for larger inputs, this is surprising, and we don't like an algorithm to be wrong. And so even if an algorithm looks really intuitively correct, it might be broken in fundamental ways. And so we really want some machinery to be sure. That's what this unit is about. And Well, to make that point really clear, never use this. I'll show you the correct one in a second. And so in terms of this question, you can see how you did. I mean, this is true for me, so the first two are not relevant, but it's true that the algorithm can produce every possible ordering. With some probability it does, but neither of the other two statements are correct. The fix for this is super simple. It's a single symbol you have to change. Instead of 0, you put an I here, and then it works. Intuitively, why that is so different, think about how a single element can travel. In the original algorithm, it could be swapped several times around if it got selected again. Whereas here, we go through every element, and then for each position I, we now decide which original element is going there. And then once it's there, it's never touched again. Because I goes up, and we don't have R below I. So after we made this swap, so for each element, we have one point in time where we decide, this is your final value. Chuck. And then it stays there for good. That's why this algorithm is good. That's why this bears the name of 3 famous people. It's usually called the Fisher-Yates shuffle. Knuth popularized it. They all deserve credit for many things. This is a fairly simple algorithm, so maybe it's all right. But that's the name it goes by. So if you ever need to shuffle, look for this one. Don't use the other one. So both of these algorithms look intuitively fine, but they lead to different outcomes. So we really want some way to tell them apart. The way to tell them apart relies on formal proofs. And there, the first step is formal statements, logical statements, and then how to arrive at the validity of such statements. So if you want to go all the way back, this is the very question that mathematicians answered in the 20th century. Only in the 20th century, somewhat remarkable. What does it mean to have a proof? Prior to that, a proof was, if it was convincing to your fellows, the other mathematicians in your guild, then it was good. And if it wasn't convincing them, it was not good. But this relied on people to be diligent enough or apply enough scrutiny to these arguments. And in the 20th century, some of the big successes are putting maths on a formal foundation and discovering the holes in there. There's some fun story around impossibility results. But what we do have is a clear understanding of what formal proofs are. And if you can prove it in that system, it's bulletproof. That's why I have this little Iron Man for the unit as well.
Isn't it possible to prove some things that are not true? Like,
is it possible to prove things that aren't true?
Like,
that would be really bad for a formal system.
Like,
there's many examples of things that look true and look like provable.
I've heard that piano arithmetic is inconsistent. Piano arithmetic is like, it's not, piano arithmetic cannot prove its own consistency. So depending on other assumptions you make, you can like prove previous things, and there are things that are true or not provable, things that are not true and provable.
Okay, so you're getting at consistent and complete systems. Yeah. Let's take this offline. We can chat about this afterwards, because I think it's for most people doesn't help much at this stage before we talk about other things, and it's beyond the module. But there's some really cool math theory behind this. It's a lot of fun. You don't need to worry about it for this module, but it's definitely worth knowing. I can talk about this at the end of the slot. So what we need, a formal proof is written in a formal system, and that tells you what kind of statements you can write to make proofs of. And so a formal proof is a sequence of such statements. And each statement can either be an axiom. That's something that everyone decides we believe in that because we decide to believe in that. There's no justification beyond that, but they're usually so clear and primitive that they're fine. And this is not usually a problem. For the experts, axiom of choice, there's some that are debated, but this is on the philosophical and esoterical end of mathematics, I'd say. There's a set of axioms that people rely on, and there's no doubt about them. And we can restrict ourselves to those for this module entirely. So and the statement is either an axiom, something that is true because everyone decided, let's rely on this, or it is something that follows from previous statements using a set of rules. And we'll see some of these in some of the example proofs. But these two things together imply if you start from valid axioms and you apply valid rules, everything you'll ever be able to write down is valid by definition. And so there's no interpretation needed or no human scrutiny needed. Some of these systems are provably incomplete, so they're true things that they cannot show. That's a bit annoying. But if you have a proof, it's not a problem. The proof is valid and the proof is rigorous. It's just sometimes you need to go outside of a specific system. So that becomes relevant if you want to prove things automatically by a computer. But that's not our topic for this module. We'll usually actually go back to convincing humans because going to this level of detail is very, very tedious. I want to convince you in this unit of that fact, and also try to show you how you can live on a slightly more abstract level, but keep the possibility of going all the way down if you have to. For example, to check in cases like for this shuffle algorithm, where it seemed to work fine, but if you look close enough, you notice one does and the other doesn't. Good. Okay, let's dive into some of the statements that we can make. And I'll use English language examples here first, just because it's a little easier to talk about. But we'll mostly have mathematical statements here later. So we can have statements. What's a statement? A statement is something you say that can be true or false. We'll usually not allow anything between. It's either true or not true, which is the same as false. Okay, there's no gray areas. And so a great example is it rains, which is already debatable if that's always either true or false. But let's pretend, right? You formalize that in some way if there's any drops reaching the ground, or I'm sure this gets hairy if you define it properly, but let's ignore this. Humans are usually good at having a sort of some vagueness we can tolerate well. A second statement can be the street is wet. Similar problem, but let's pretend this is very clear and always true or not true. If we have a statement, we can negate it. Then instead of the statement, we have not the statement. So not A is not it rains. We usually say it doesn't rain. Logically the same thing. We can put and or between two statements. A and B, it rains and the street is wet. Both have to be true for the whole thing to be true. And or means, well, either of them can be true. It's okay if they are both true. So this is not an exclusive or. Sometimes it's useful to have the statement it's either A or B, but not both in one thing. As you notice, English doesn't really have this. We often use or in the sense of exclusive, not both, but not always. And if you want to be very clear, you have to wiggle your way around and say it explicitly, either A or B and not both. It's sometimes convenient to have a notation or an operator for that, and XOR is the thing that people use for that. I don't know if we'll ever use this. I've seen this notation many times for Boolean logic reasons, but well. So this statement is true. A, X, or B is true if either A is true or B is true, but not both. And also not both false, please. Clear? Okay, the more interesting ones are implications and equivalence that builds on it. Implication is written as this: A arrow B. A implies B. In English, we would say if A holds, then B also holds. Something like that. If A, then B. And this is really equivalent to not A or B in case of doubt. We'll come to that, but here, if I insert what A and B means, it becomes relatively intuitive. So if it rains, then the street is wet. Sounds good. Equivalence is one step further. It says A and B are really either both true or both false. So A equivalent to B means A holds if and only if B holds. And because this is something we use so often, mathematicians have invented this if with a double F to mean if and only if. Just the if is implication. The only if, A only holds if B is true, is kind of the reverse implication. So that's why you can also define this A equivalent to B by having both implications. A implies B and B implies A. Yeah, question?
About this.
Yeah.
Okay, so you have like two statements, P and Q, at the correct position, A and B. Then if A is a necessary condition for B, then I say A implies B. That's what A is a necessary condition for B. Then if A is a sufficient condition for B, then B implies A.
Yeah, okay, so these are two useful terms, necessary and sufficient conditions.
If A is a necessary and sufficient condition for B, then A if and only if.
Yep.
Yeah, and another way to think of it is if A implies B, then the set of statements where A is true is a subset of the set of statements where B is true.
Yep.
Right? And vice versa. And if, yeah, that's like, I find it an easier way to think of implication and equivalence.
Yeah, that's right. So there's alternative names for these if you want. A implies B. We sometimes say A is a sufficient condition for B. If A holds, then B already holds. And the other way around, B is a necessary condition for A. If A is supposed to hold, then B better also hold. It's another way to phrase it. I mean, yeah, it's more intuitive for some people, and others like the implications more, or you think in terms of Venn diagrams. You have to find your way. It's something that this book gives you all the different variations of, and you can pick whatever you find more intuitive. Now let's do a little exercise on this one. Where's the question? Sorry, now it's showing. It's annoyingly slow. I don't know. Slido has a problem today. I should have probably hidden this. All right, let's have 65 again. I hope we don't have too many flat earthers in here. All right. Show it again. Okay, well, because I give participation marks, I shouldn't lock the questions too early. So it's roughly 2/3, 1/3, maybe a bit more for yes, but a few for neither as well. So this is a true statement in the logical sense. And the good thing is it doesn't depend on whether you believe the Earth is flat. It's simply implications are always true if already the premise is false. And that becomes obvious if you say, let's decompose this into our statements. That's statement A. If A, then statement B. Now maybe we can agree that B is not true, but doesn't matter. A implies B is the same as, maybe I'll write it like this, not A or B. That's just the definition of implication for us. That's why I'm bringing this question. So if A is false, and we believe A is false, it doesn't matter what B is. If B is true or false, we don't need to care. Good. With the terminology set, let's have a look at a few proof templates. And these go step by step through different kinds of statements. Any statement has a different template that you can apply, or a set of templates. The most interesting type of statement is the implication, just because it pops up in different other statements, and it's just the most commonly found one. So if we try to prove A implies B, we can just try a direct proof. We start from A. Remember, a proof is axioms and inference and statements derived by inference rules from previous statements. If we prove an implication, we start with the axioms and A. That's also something we can start from. And so a direct proof would try to derive B by following through these steps, starting from A and the axioms. That's the obvious thing to do, but you can also do slightly different things. You can reformulate the statement first. If you go back to this equivalence, then you find that A implies B is logically exactly the same as not B implies not A. And sometimes it's more convenient to do such an indirect proof, or fancily called proof by contraposition, because you swap these two things around. Before, I could start with A and try to prove B. Now I can kind of go from B to A, but I have to negate things. So I start with the negation of what I want to prove and try to show the negation of what I start with. So we could try, yeah, we'll see examples later. Slightly related, but a little different in the way you carry out things, is a proof by contradiction. So you assume that the statement you're trying to prove is not true. And that comes down to assuming that A is true, but B is not true. So if A were true and the implication is true, then that would imply B. So we're assuming something that we don't believe. And then you try to derive a contradiction from that. So you try to arrive at a point where you have, I don't know, x equals 5 is one thing, but you could also show x equals 7. And so these two things contradict each other, which means one of the premises must have been wrong. That's another way to show implications. That's often, well, maybe this is something about human nature. I don't know. It's often easier to find contradictions than direct proofs. I don't know. Yep.
So, probably by contradiction, like, if an implication is true unless you have a true statement implying a false statement. A implies B is true unless A is true and B is false.
Sure.
So if you want to prove a statement S is by contradiction, you can assume not S, that not S is true, and show that not S implies something that is false. So if not S, if a true statement implies a false statement, the implication is false. So you know that if not S implies false, you know that something is false, so that unequivocally false, like X and not X, or
sure.
0. You know something that is false always, and you know since the right-hand side is false, and the implication is also false, then the left-hand side must be false. Because false implies false is valid, but true implies false is wrong. Yeah,
exactly. Okay, so I mean, to summarize this a bit unfairly. You can apply proof by contradictions to all kinds of statements by just negating what you try to prove and try to arrive at the contradiction. It's just for implications, usually, well, it's maybe less obvious and often effective. Yeah, let's try to get through some of these things, because there's a few things I want to touch on later. Another thing that's very versatile and often helpful is to distinguish cases. It just happens that sometimes it's easier to make your problem harder. Instead of doing one proof, you do two, but each of them is easier. So you have some other condition C, and you can have A and C, or you can have A and not C. Those two together are everything you can have with A. But sometimes the arguments get easier if you have additional ammunition. I'm sure we'll find some examples later in the module for this. The important bit here is that it has to be an exhaustive case distinction. You have to cover all possibilities. That looks super obvious when I write it like this in terms of these logical formulas. It's much easier to lose some case when you're folding this up into a big proof. So it can help to spell out explicitly. I'm looking at, let's do a case distinction. I'm looking at this case now, and there should be a last case, everything else. Then you have covered everything. Let's do another quick example, just to see if this made sense to you guys. Oh, come on. So you take your time, I'll just start writing some things. All right, I think we have. Is anyone still voting? Can I lock it? Never mind. I mean, you can cheat and change your answer, but you don't gain anything from it. So it's an indirect proof if we do this. Come back to it. I thought it's helpful to actually do the full proof, just to show you a quick example. So it's not a super important statement for algorithms, but well. So if n is odd, that means we can write n as 2 times k plus 1 for some natural number k. That's the definition of odd at the end of the day, and depending how you formulate it. So this n0 is just the natural numbers 0, 1, 2, and so on. And then if we have that knowledge about n, we can have a look at what n squared looks like. And then that's just a little bit of algebra, arithmetic, depending how you want to phrase it. And we arrive at something where n squared has the same form. So that's some number k prime. The important bit about this is that k prime is 2k squared plus 2k. If k is an integer, then this k prime will also be an integer. We're just doing operations that stay in the integers. So that one, again, is a natural number. And that implies n squared is odd, because we've written the number in the shape that is required for odd numbers to exist. 2 times something plus 1, right? Apart from the usual type of miscalculations when I do this on the spot, that's the proof that is meant in this question. And if we want to highlight why this is an indirect proof, we can split up the individual parts. So that's our statement A. That's the statement B. Now we showed n is odd implies n squared is odd. That's the same as not B. It's just slightly hidden because I changed from odd to even. But for integers, it's either any integer is either odd or even. So not even means odd, as odd as it sounds. And that's not A, right? So we showed the implication not B implies not A, and that's an indirect proof. Questions so far? That's what I mean by templates, right? You start with a statement like this, and maybe it's obvious for you if you think about a few examples. Writing down a rigorous proof is actually quite challenging, even for these very simple ones, or maybe exactly for these simple ones. And having the right proof templates at hand, you could just go through them, and often one of them is applicable. And here, this turned the task into a simple computation, because we could take the knowledge, n is odd, get some tangible thing out of it, write it as 2k plus 1, and then do something with that knowledge. Other types of statements that we will often meet are these. And these will be, I'll go through these quicker because they're usually falling back to what we already know. If we want to prove that A, if and only if B, this equivalence, we know that that's actually just 2 implications. So it means we have to prove 2 implications separately. And most of the time, that's the easiest way to go about it. It makes the proof twice as long, maybe, at least logically, but usually it's much easier to prove an implication than to directly prove an equivalence. So whenever you see an equivalence and you're asked to prove it, your automatism should click in and say, OK, I have to do these 2 things, prove 2 implications instead. Apart from combinations of logical statements, we'll often talk about sets and other kinds of mathematical objects that reduce to sets at the end of the day. And one of the simplest is we can have a set of some objects S and another set, and we may want to prove that R is a subset of S, right? You know this symbol, I hope. That's the subset relation. It means every element in R is also in S. You can rephrase that as an implication. If you want to be picky, we should have a for x, for all x in front of this. We'll talk about these weird quantifiers in a second. So you can rephrase a statement about sets as an implication. And we know how to deal with implications, don't we? We can also sometimes want to prove that 2 sets are equal. But S equals R is the same as S is contained in R and R is contained in S. So again, we can go back to implications all the way through, and we know how to deal with those. That's my assumption for now. I think this is a good moment to take 5 minutes break. these 2-hour slots are a bit brutal. It's arguably not possible to focus for a full hour anyways, but 2 hours is pushing it for sure. Let's say we start 12:05 again.
Oh,
Yeah.
probably. This is Monday class.
Okay, no worries. Yeah.
Yeah. Really even like getting a fundamental understanding of what competition is, how competitions operate, like mathematical model. Yeah. So I've been doing from trying to learn about logic and
Yep.
stuff like that.
There's a really nice Veritasium YouTube video about the inconsistency of mathematics. I don't know if you've seen that one. I wanted to send this to Campusfire because it's very nicely done as a nice background about the things you alluded to.
Oh yeah.
What was your name? Were you?
Toby.
Okay.
Yeah. Sent an email that
Yeah. Okay.
just arrived.
Yeah. No worries. I don't know about the university attendance system, but I think they're trialing this anyway, so we can just blame it didn't work. Are you guys having problem with mobile internet in here? Is this? Some have problems? Yeah, at your room might be a better option. I tried once to live stream over Eduroam and decided I need Ethernet cables. It seems a few people are still missing. Give it a minute. We could discuss this question from before. I didn't see that pop up at the time. It's true that random int could get the could return any number, including I, the lower bound, and that would mean that the swap is basically stepping on the spot. Yeah.
Yeah. So what we wanted is something that will give each ordinary equal probability.
Yep.
And of course, there are some ordinaries where the elements will be exactly the same.
Yeah. That's true. Yeah.
We don't want to prevent that from happening.
Right.
We also want that to be any more likely than the other one.
Exactly. So that's why this is not a problem. Even leaving the list by chance with a small probability in the exact order you have been given, that's all right. With 1 over n factorial, that's supposed to happen. Just please be uniform. All right, guys, let's continue. I hope you have some steam left. I say the more interesting part is yet to come, but we'll go nice and slow. I do want to, I'll try to leave a little time at the end to discuss the prerequisite survey. But that can take as much time as we give it, whereas I want to get through the material according to the schedule. Yeah, if we only can touch on this briefly, there's no harm done. It's mostly for information. Yeah, let's talk about mathematical induction as one of the slightly less obvious proof techniques or proof strategies, which at the same time can be very powerful, specifically in discrete mathematics and computer science. Induction is all about quantified statements. I've briefly alluded to this earlier, but let's introduce the notation and the notions for that properly. Because this is, again, something that pops up many times and is very well worth knowing beyond this module. The first thing we need is statements that have a parameter. So it's basically a placeholder for something, some object, a number in this case. I'll write a of x for a statement that has something to say about this value x. And that could be, from our example, x is an even number. Now, obviously, such a statement can be either true or false depending on the value of x. So it doesn't make sense to say prove a of x, right? I can prove a of 4 or a of 7. But the statement a of x itself, if you want, it's more like a function. For every value of x, it tells you a Boolean value, a truth value, yes or no, true or false. But not by itself, it is it true or false. We can turn it into a logical statement that has a true or false value using these quantifiers. And they basically tell you what you're supposed to do with this variable x. And there's two that are really useful. Existential and universal quantifiers. Existential means there must be some value of x so that a of x is true. There exists some x so that a of x. And we write this with this little reverse e. I don't know where the symbol comes from, but it seems a good mnemonic to say e like exists. Exists x so that a of x holds. And the other one, don't ask me where this symbol comes from, is this little angle. I don't know. Pardon?
Upside down A.
Upside down A. Yeah, that's a good one. Yeah. Okay, like that. Yeah, how could I not miss this? Thanks. Okay, upside down A stands for all. It stands for all. Either way, for all x, a of x should be true. Now you can immediately imagine that that kind of statement is very relevant for algorithms because we usually want to say they are correct no matter what the input is. That's saying for all inputs, the algorithm does the right thing. And we'll have to talk about the second bit, what that means. So yeah, let's highlight that a bit. These are the statements we very often deal with. As often with these logical statements, it can be convenient to have all of them just to be more expressive, but we could do with just one of them by rewriting. Saying that A is true for all x is the same as saying there's no x so that A is not true, right? I think that's intuitively clear enough. So you could always just use for all or just exists. Now the tricky bit is when we start to nest things. You can have statements that have not just a dependence on one variable x, but on 5 or as many as you wish. And that's where things get really powerful, but also a little complicated. And we have to be careful about the order of the quantifiers. I wanted to put a real example there just to make it clear, even though, okay, I hope that most of you have seen the formal definition of the limit of a function or the limit of a sequence. In this case here, what we're talking about is some function x. It takes a value and it spits out a value. And we could try to prove some properties of that function, like continuity, or is not an analysis class, so don't have to get into this in much more detail. But we want to say as x approaches some specific value, psi is some number that you fix, it's not a variable. As x approaches this value, the function value approaches some other number, a. Okay. We'll often use this for asymptotics. We'll see next unit, so not much use to talk about it now. We'll use this full stop. What does this mean that the function has this limiting value? This is one of the things where historically mathematicians played with this for a long while with infinitesimals and trying to do this intuitively. I mean, it's probably fair to say that in some instances they fell flat on their face by not having a rigorous notion for this. And what people came up with as a rigorous notion for the definition of this limit is this, the epsilon delta criterion. It says, you tell me for every epsilon, how close do you want the function value to be to the limit value? You tell me how close you want it. There exists a delta. I can tell you a delta so that if x is closer to psi than delta, the function value is closer to a than epsilon. So nested quantifiers often can be phrased as this kind of game. For all means opponent's choice. You have no control. Exists my choice. I can pick one. Now the tricky bit is the order matters. Having you choose first and I can react to that is different from you choose first, I choose first, and you can react to me. Very obvious in games. Who starts matters. And so for quantifiers, you have to read them left to right. Another way to say this delta is a function of epsilon. It may depend on the choice of the quantifiers to the left. Okay? All right, we won't really talk about limits of continuous functions very much. We'll basically apply this for asymptotics. How does a function or an algorithm behave if n becomes very big? In that sense, we'll use limits. This is more for background and just to make very clear. These quantifiers can be nested, the order matters, and the inner variables can depend on the choice of the outer ones. Okay. Pardon? Sorry, I didn't get that. Yeah, it's the way to build powerful statements. For example, here, okay, let's move on. Simple statements to prove are the existential ones. If you have a statement exists x so that a of x, you just find one x and be merry. That's often simple because you get to choose what the value is. And so it's a simple proof as the ones in the previous subsection. The trickier bit is the for all statements. And that's where we go to the main topic of this section. So let's see how many of you have seen this before.
Sorry, excuse me.
Yep.
For all the negation of an existential
Yep.
statement, so you can prove it by contradiction. Okay. Why
Yeah, you
is
can
induction
prove it by contradiction.
preferred to prove by contradiction for universal proof?
Yeah, okay. So I guess the question would be if I claim for all is hard, why don't we just rewrite as an existential? We could do that, and then we have the negation. So we could do proof by contradiction. The thing is, you would have to prove that any choice leads you to a contradiction, and that any choice that seems hard, right? Whatever choice you write down, I could say, okay, it failed for your choice, but I have a different one. Maybe it's fine for that one. So you still have this. I have to go through all cases. I don't think you can get rid of that. Induction is a way to get rid of that in a specific sense. You'll see. Good. I think that's enough. A lot of people have seen that. So maybe yeah, maybe I'll do an example, but a quick one then. You'll do an example in the tutorials, but let's first talk about the statements. So we're talking about for all statements. These are the tricky ones. For all x, a of x. And now I'm thinking of x not being any real number, but it has to be something discrete. So the easiest case is natural numbers. Okay? So the statement here has to say something about natural numbers. Yep.
Couldn't you do induction over the view, not like interval? If you could prove that an interval of a certain size, it made it like instead of if you could show that a particle for an interval, then couldn't you do induction over intervals to prove something over the entire real numbers or something? So that one.
Okay, question is, can we somehow rescue some bits of induction for the reals?
Yeah.
I mean, depends. Let's first talk about induction. If the statement is fundamentally about continuous things, then no. But there might be sometimes tricks. I don't know. I think the answer is no. If you can, then you can reformulate the statement. So sometimes we write this restriction as for x in n0 or something like that. So that's, if you want, it's a shorthand for saying for all x, x in the natural numbers implies a of x. Okay. That's logically the same thing. This is more convenient to write. So we often, in a way, this is about mathematicians and types. Often doesn't go well together. Mathematicians are very, very sloppy when it comes to types compared to programmers who are used to the strict typing of most programming languages. So when a mathematician writes for all, it's usually assumed that the reader, the human on the other side, knows or figures out what the possible values for x are. It often doesn't make sense that here x is a square or a motorbike. You usually have a clear notion of what x can be, and it's not a sin to express that implicit thing explicitly. Right? What is the set that x can come from? That said, I'm also sometimes sloppy, and it's convenient to leave things out if you don't have to write as much. So I'll sometimes write things like this as well, in the hope that the range is clear. But it should always be possible to write down the exact range without thinking too hard. What does induction do? Induction does two things. You prove the statement you want to prove for some, sorry, that's not the part of induction. One way to prove a for all x, a of x statement is you prove the statement without assuming something about x. That's sometimes possible. Sometimes it's convenient. I think it's mostly, it's a bit dangerous. Usually you need something about x. So this is in principle possible, sometimes doable, a direct proof. It's a bit dangerous. Induction can be a little more convenient. Yep.
Yeah, like something like can prove that x or not x is true for all number guiding inductions. Like for an arbitrary x or not x is true. You don't have to like this induction to prove something like that. Things that like are contradictions or tautologies.
Yeah, I see. Okay.
Using guiding induction.
In some easy cases, when you see that the statement doesn't really depend on x much or something like that. Yeah. Yeah, so that's why I listed it. Sometimes it's doable. Induction is a way when it's not so easy. And there, if we have, say, the natural numbers from 0, we would prove as one thing the statement for 0, and then prove a different for all statement, but one that gives us more ammunition to prove. We prove that for every n, if we have the statement for one number, that implies the statement for the next bigger number. And those two things together are enough to prove the statement for all natural numbers. And people often draw a ladder where you start at 0, you build this first little piece of the ladder, and then you show whenever you can build a ladder up to a certain height, you can get the next higher one by adding one more pole. And so you start with 0 and you prove that you can always make a step. And by always making a step, you get to any fixed height. Okay. That's the principle of induction. In this strict version, you're only allowed to use a of n to prove the next bigger number. This is actually a bit restrictive. You can also just use all previous statements. You use that the statements are true for all values up to the one that you currently look at, and then prove the next bigger one. Sometimes people make a distinction and call this simple induction, weak induction, and this strong induction or complete induction. I don't care too much. It's both induction. There's not too much of a magical difference. You can extend the principle a bit more. We won't really need that here. But you can essentially apply induction whenever something is constructed step by step. You can start from something and then you can make it bigger. And maybe a natural thing for us in computer science and in this module, we'll talk about binary trees. So one way you can apply induction there is you can say a binary tree is a leaf, or it's a node with two subtrees, which are binary trees. So that's again a way you can start from one thing and then build up. If you can do that, you can imply induction. Question?
I think the distinction, because, well, in one other set is just basically and a set for which any subset has the smallest value. I think that's like an easier ordered set for which ordered sets for which any subset has the smallest value.
Yep.
Which subset has the smallest value, then that's where ordered sets. Like order. Then I think the distinction between the strong and the weak induction is proving an plus 1 by only from an and proving an plus 1 from multiple previous statements might be different. It might be cases that maybe an alone is not sufficient to prove AM to its one. I don't know of any simple examples like that, but some like more complicated statement for which more complex sequences for which the next value, if the next value does not depend only on the previous value but on all previous value, we're able to prove it using only the previous value. Right?
Yeah, I think the distinction between this weak induction and the strong induction is a little academic if you want. I think you can reformulate your statement so that it includes all the previous ones, and then formally you apply the other induction if you care so much. I don't think that's the key thing here. What's surprising is that you can basically bootstrap yourself. Inductive proofs, sometimes when you read them, you look like, yeah, I think that's solid, but I've learned nothing about the statement, apart from the fact that you've formally proven it, right? Which is remarkable. Often a proof is assumed to convey a lot of knowledge and insight into what you're proving something about. Inductive proofs need not be like that. They can be completely ugly in the sense they teach you nothing, but they work. And I mean, if the goal of a proof is to prove something, they're really effective. So yeah, sometimes it's much easier to come up with an inductive proof than any other proof. Shall we do a quick example? What are people's thoughts? I guess there's 2/3 that say, don't bother me. I've seen that. And the other third's a bit lost at this point. I'll do a compromise. I'll do an example and run through a little quick so that we can cover the rest. Let's see. I think a nice example is the Towers of Hanoi. I think many will know this. So it's a puzzle. It has some story behind it, but I think this is all made up by mathematicians. And so without, think of your favorite mystical setting, an Indian temple, some Vietnamese thing, or what else? I've read it in a monastery and some hideaway place high up in the mountains or whatever. The game has 3 poles and has disks sorted in size, and the goal is to get the entire pile to a different pole, but you can only move 1 disk at a time, and you're not allowed to ever put a bigger disk on top of a smaller disk. And then usually the story is, well, these priests, monks, whatever, they have to do this, and once they finish, the world comes to an end. And well, whatever. So the most original story I read was that they have 64 pieces stacked on top. And so when they finish this, the world comes to an end. And the question for you is, should we worry, right? So let's try to answer that question. How many steps do we need to move this 64 pile from one pole to the next? If you've seen this before, okay, I know it's maybe has lost its magic. If you see this for the first time, you start playing with 3 or so, and you figure out, yeah, okay, you could do this, right? You can put the top one here, and it's gone from there. Then you can put this one on the other top. Now you're all blocked, but you can get the smaller one from here, put it on top there. And then I can actually move this lower one to the last position. Now I have to think a bit ahead. If I place this here, I can go with that one there. So let's take the smaller to the side, middle one up here, and then finally that one on the top. Good. Easy to do with 3. If you do it with 5, you get already a bit bored and lost, and you move a few pieces around because you messed it up. If you do it with 64, how many pieces? What's the minimal number of steps? Does anyone know? You remember? Minimum number of steps? Pardon?
some time to think with the question?
Unfortunately, not this time because, well, we could do first the other. It's hard to spoil a. I feel for you. It's annoying to spoil a puzzle, but I think I have to. So let's transform that into an inductive statement. We want to say about something for all sizes. It's kind of easier to solve the general than the specific one in this case. So let's say we have n disks. And I'm claiming the number of steps we need if we have n disks is, drum roll, 2 to the n minus 1. And so as a computer scientist, you should know that 2 to the 64 minus 1 is not to worry about. So integer overflows, if you count up in a loop, a 32-bit integer you might see overflow. A 64-bit integer you will never see overflow in this universe. So that's the answer to the very practical side of this puzzle. The poor monks will never finish. I think it's 500 billion years or, well, something like that. Takes basically forever in physical terms. But how would we possibly prove such a statement? By induction. So we would start with the induction base. The base case is, let's be really lazy. Let's say no disks. I have not to do anything, so the answer should be 0. 0 steps are needed. And 2 to the n minus 1, that is 0 if I put in a 0 here. Brilliant. So that's the base case done, right? And now we do the inductive step, which is, I'm assuming, the inductive hypothesis. That's how people often call this. That's the AN. And this is our statement A of n. So let's assume that we already know for n disks, it's exactly 2 to the n minus 1 steps that I need. And now comes the brilliant little insight. If I have my tower, there's one more disk at the bottom, and then a tower of, okay, this is even below my standard of drawing. That's gonna say something. How do we move this pile of disks from here to here? Well, 3 steps. We take this large bit, move it here. That's step 1. Then we move the red part to here. That's step 2. And then we move the gray one back. Easy, right? 1, 2, and 3. How many steps do I need for that? The red one is a single step, easy. The other 2 are the inductive thing with just n, one smaller. So if we start with n plus 1 disks, then the number of steps for n plus 1 disks is 2 times the number of steps for n plus 1. And the rest is arithmetic, because now we can use the inductive hypothesis to replace this by 2 times 2 to the n minus 1. And then you see that this works out to 2 to the n plus 1 minus 1. Right? And that's the end of the proof. You see, in this case, you actually did learn something about the problem, because this is a recursive algorithm, and you could actually implement it by a recursive function just like that. No much thinking needed. But also, see how knowing the solution for the one smaller problem was really all we needed here, and the proof became quite simple. Whereas if you try to prove all of this directly from nothing, it's also doable for this puzzle, but it's more tedious and needs more insight up front, whereas the induction here guided you to what you had to do. All right? Good. That was Towers of Hanoi in 5 minutes. Yep.
In this case, we use induction to verify the solution when we did.
Haha, yeah.
Is it generally because things that you can verify inductively, you can also discover, like, let's say we're going to know the answer to this solution, not to verify it. Would it have been able to, like, figure out the answer? Would it have been helpful to, like, discover the answer?
Yeah, so that's a good point. So the question is, can you somehow, instead of just using induction for proving what you already know, discover what you want to prove? I think it's the Achilles heel of induction is no, not really. Usually induction doesn't help you discover what you have to prove. Sometimes it can work iteratively. You try with some statement and you try to prove it, and then you see you're stuck, you're missing something. And that can sometimes give you the insight of what that missing bit is, and then you can add it to the statement, and then it goes through, but it's not really like a clear structure. Yep. Induction doesn't really help you much if you don't know what to prove. It can just be super terse and quick if you do. Okay, as a last little bit, let's briefly apply this to proving some things about programs and algorithms. The bigger picture here is there are some applications where you really want more confidence in a piece of code than the programmer said, yeah, it looks good. And that's where formal verification can be applied. So you formulate in these kind of statements for all x exists y and all these things, you formulate what the program should do. And then you try to formally prove that. We won't do that to the full detail because it gets very tedious and is quite a topic of its own. But we'll touch on two things that are usually necessary for that. Correct usually means two things. First of all, the code actually finishes its job eventually. And if it does, then it computes the correct result. So I'm thinking of systems that have a clear input computation, output behavior. They compute some function. There's other theories about other systems that continuously run and fulfill some purpose. This is not what we're talking about. In a way, the formal verification we need here is there's something that you assume at the beginning of the program, then the program runs and does its job, and then at the end something should be true. So that's precondition and postcondition. That's what we usually have in mind here. So there's some assumptions that the algorithm makes. For example, the parameters of a function, the input value has to be a positive number. Then the code executes something, and that leads to a postcondition that hopefully has some value to you. We'll see examples. For the first bit, I just want to briefly touch on how you can do this. We'll do some example in the tutorials then. Suppose you have some function, a procedure in my Pseudo Code lingo that is recursive, so it calls itself. It could be our Towers of Hanoi solution, for example. And you want to prove that it eventually stops, right? A recursive function could keep calling itself. The formal way to prove that is to define a potential, some quantity that keeps going down but cannot go down indefinitely. So the important bit here is that our potential is a natural number. And natural numbers famously stop at 0. There's no way to go further down. So if you can somehow prove, I should have mentioned the parameters. So the potential exactly depends on the parameters to the function. Say in our Tower of Hanoi example, you call it with the number of disks that you want to move and probably also where they are. So what's the current pole that they lie on and what's the target pole. That's the parameters of the function. And then the potential can depend on those parameters. What you try to prove then is whenever the function calls itself recursively, like Tower of Hanoi, move this there, then do the red move and then move it back to the middle. In all these cases, the potential drops by at least 1. It strictly goes down, and because it's a natural number, that means it drops by at least 1. Okay? So example from Towers of Hanoi, the potential could just be the number of disks. Whenever we call ourselves on a stack of disks that's 1 shorter. That proves that we have to finish with this recursive call eventually, because we always go 1 step down. So at some point we reach no disks, and then the procedure can just return. Okay? The idea is more versatile. The potential can be more complicated and depend on the parameters in interesting ways. You'll see an example in the tutorials. Yeah, I think that's basically all on this potential. It's just a convenient way to make the notion rigorous. That's when you recursively call something, you should somehow make something smaller. You can apply the same trick to a loop instead of a recursive call. If you have a while loop, might never finish. But if you can show that some potential function that's defined on the variables of the code there goes down in each iteration of the while loop, then it must terminate. Okay. The second bit, this is about correctness in the sense of computing the right result if it terminates. In this case, we'll talk about these pre and post conditions. And I picked out the most interesting case of that. So often pre and post conditions, they say something about the values of variables. And for simpler statements, like if the statement is x is assigned to x plus 1, increment x by 1. Then if the precondition said something about x, you know what the post condition will be. It says the same thing, just where the value of x is updated. So if the precondition was saying x is at least 5, then the post condition would be x is at least 6, right? If we increment x by 1. These kind of statements, there it is easy to go from what is true before to what can we guarantee after. It gets very tricky with loops. And that's the example I want to pick out here. For a general loop, a while loop, you need to work a little harder. So the setup here is we have some position before a loop, and we know there's some assumptions we make what is true before the loop. Then we have a while loop with some condition, it does something, and then we want to guarantee some statement after the loop. I'll have a more concrete example on the next slide. I wonder if we have to push the example to next week, though. Let me walk you through the sequence of steps you have to do in this case. The trick here is to find some condition called loop invariant, for which you can prove a few things. You can prove that it is already true before the start of the loop. It is true again after the body of the loop, but here you can assume that you are in the loop. So you can additionally assume the condition of the loop to be true. And you also want to be able to prove that the same invariant is true after the loop. That sounds a bit abstract, I guess, right? But that's a way it's a formal strategy. Whatever I is, if you can prove these things, then you can hopefully get some desired postcondition. Let me at least show you the concrete example. And I think we'll do the proof applying the principle here we'll do next time. This is a little innocent function that takes an array and finds the largest value in the array. And how would you do this? Well, not too hard. You start with you keep the current value, you go through the list, and you always store in the variable what's the current largest. Okay. And so current maximum, I guess the name suggests it, holds that current maximum. And so initially that's the first element. And then we do a loop until we haven't reached the end of the array. We check if the current element in the array is bigger than what we previously had as the maximum. If so, then that should be the maximum, at least for now. And otherwise, we don't change it. And so you run through this, and you eventually return current max. You probably agree that this code is super easy, and it's quite obvious that it's correct. However, we've already had obvious code, and it wasn't correct, so maybe we should be careful. In this case, it is correct. There's no hidden nastiness. But what I want to do is walk you through the precise steps if you need it to show very rigorously that this computes the right thing. And often along the way, we notice that there are some corner cases and side conditions that are easy to miss, like calling this function with an empty array is not a good idea, right, if we access the 0th element. Question?
It seems to me that this technique for proving correctness of iterative procedures is generative. Like, if I want to design an algorithm to do something, I can use this invariant technique. I can like construct my invariant. I can like pick something, ensure that property is true before the iterative sub procedure, and then construct the iterative sub procedure such that the property remains true, and ensure that property is true after. So like I can use the proof technique to generate a correct algorithm to something. Like using the invariant.
Okay, so this, yeah, I mean, the question is maybe a bit two questions. So one is, can you automate the proof? Can you automatically find the proof? And can you use that to find the algorithm, right? Yeah, so it's the tricky bit in this case, the part that is not automatic or where there is human insight needed fundamentally is finding the loop invariant. There's nothing in the template. If you check here, this template lists a few things. I want this and this and this and this. It doesn't tell you how to find the loop invariant. And the reason is no one knows a strategy to do that automatically. It seems not so easy possible, at least not in general. It seems not possible to tell a computer these are the steps, then you have your loop invariant. In some limited case, it's definitely doable, but not in general. And also what happened to me when I wrote up this proof, I had the first part of the loop invariant and was missing the second. And then you notice you're somehow stuck and you need to add something else to the invariant. Yeah, I think we should come to a close, and I don't think I can do this in 1 or 2 minutes. So let's postpone the detailed example for next week. Yep. Sorry, that was not loud enough.